What is the integer equal to root 25 plus root 49 all squared? Root 25 is 5, root 49 is 7, all squared. That is 12 squared, and 12 squared is 144. How many odd integers are there between 13 over 2 and 37 over 2? 13 over 2 is 6.5, and 37 over 2 is 18.5. So we want to find odd integers in between those numbers. So it would be 7, 9, 11, 13, 15, and finally 17. So how many did I find? 1, 2, 3, 4, 5, 6. So 6 is the answer. If 3w is x, 2x is y, 5y is z, and w is not equal to 0, what is the value of z over w? So 3w is x, and 2x is y, and 5y is z. So 2 times x, I'm going to concentrate on this one. X is 3w, so put that in there. So that means y is equal to 6w, correct? And then on this side, we got 5y. Well, y is 6w, so z is equal to 30w. And then coming back to this, z over w, therefore, would be 30w over w, and therefore that is just 30. Define a new operation, diamond, by a diamond b is ab plus a plus b. Given that 5 diamond x is 41, what is x? So 5 diamond x is 41. So using this definition, that would be 5x plus 5 plus x is 41. So 6x is 36, and therefore x is equal to 6. In the diagram below, two identical squares overlap to make an 8-sided figure. The region where the squares overlap is shaded and equal to 1/3 of the area of each square. What fraction of the area of the 8-sided figure is shaded? So this shaded area is 1/3 of the area of the square. So if the area of the square, let's say, is 3, so if you have a square and its area is 3, and then there's an area in there that's shaded, and that's 1/3, so that would be equal to 1. And then the other parts are equal to 2, right? So similarly, let's just say that's 1, that would be 2. And because of the symmetry of this diagram, this unshaded area is also 2. So then what are they asking? What are the fraction of the area? Oh, okay, so the shaded area over the entire thing. So the entire thing is 2 plus 1 plus 2. So 1/5. And I think that's it. They're just asking for a fraction. A car traveled 360 kilometers in total during the first 180 kilometers. Its average speed was 45 kilometers per hour. During the second 180, its average speed was 90. What is the average speed for the entire trip? So we use our famous speed is equal to distance over time formula. Our total distance is 360. And then we have the first part of the trip. And we have the second part of the trip. So let's see what we have in terms of the question. So the first part, the first distance is 180, right? And this first speed is 45. The second distance is also 180. Second speed is 90. So let's calculate the time for each of these. So the time is equal to distance over speed. So that's just going to be 180 over 45. And I believe that's 4. And on this side, the time, we can call it T2 if you want, is again d over s, which in this case would be 180 over 90, which is just 2. So that means the total time is this 4 plus this 2. So that's 6 hours. So the total, or I guess average speed, would be speed is equal to distance over time, where the distance is this guy, and the total time is this. So that is 60. And To make it complete, put in the units, kilometers per hour. The letters A, B, C, D, E represent digits 1, 2, 3, 4, 5 in some order. A, B is 2 digits, tens digit A, units digit B. C, D is also 2 digits, and B, E, D is 3 digits. Given that A, B times C, D is B, E, D, what are the digits A, B, C, D, and E? All right, so this to me is, oh boy, I think this is an experimentation type of question. And let's see what we get. I'm hoping that it's quicker rather than longer, but let's just see. So we have AB times CD is BED, right? So if we expand this, we basically are getting 10A plus B times 10C plus D, and that's equal to 100B plus 10E plus D. Correct? Okay. So now we have to expand this again, and yeah, unfortunately. So we got 100 AC plus 10 AD plus BC plus BD, and then the rest is the same on this side. Okay. So let's compare. So this guy and this guy, let's compare that. If BD is indeed equal to D, then that basically means that B is equal to 1, right? But I don't know if that's true. Now let's see if that works. We know that this side here, if B was 1, then that would be 100 plus the maximum would be like 90 something. So this side has to be less than 200. And on this side, the smallest it could be is, let's say, if 1 is taken already, and each of these digits has to be used only once, I believe, right? Yeah, so if you just use 2 and 3, that 100 AC would become 6. So that's going to be at least 600. So that doesn't work. This doesn't jive. So sadly, B cannot be 1. Yeah, that's unfortunate. But if we try something else, let's say, see this side here, it's got a lot of 10s in it, right? So I'm thinking like multiples, something that would add up to a multiple of 10. So, for example, if we let B equal 3 and D equal 5, then BD would equal 15. And then this might work, although this is not correct. If we split it up, then this could get absorbed into here. Where is it? The BD. Yeah, this could get absorbed into this part. Does that make sense? And then all you'll get is this 5, and that 5 would be the standalone. I think that would work. I'm pretty confident about that. So let's go with that. Let's stick with this. B equals 3 and D equals 5. Yeah. Okay. Let's see here. So the 3 is gone and the 5 is gone. We've assigned those to B and D. Okay, so now we just have to figure out the other 3. Okay, well, I sorry I have to move this up. Okay, so let's substitute those back in. So we have 100 AC plus 10 times D was 5 plus 3 times C plus BD, which is 15, correct? And then on the other side, 100 times 3 plus 10E plus 5. Okay. So I have less letters, that's always good. 100 AC plus 50A plus 30C plus 15 is equal to 300 plus 10E plus 5. Okay, now let's see here. Can we collect any like terms? 100 AC plus 50A plus 30C is equal to 290 plus 10E. Okay, so we have A, C, and E, and the numbers we have left are 1, 2, and 4, correct? Yeah, because 3 and 5 have already been taken. So I guess at this point we just have to fiddle around with this. I don't know if there's any mathematical way of doing this. So let's try A equals 1 and see what happens, and C equals 2. So if A equals 1 we have, and C equals 2 we have 200 plus 50 plus 60, and that's 290 plus 10E. So that's what, 20 is equal to 10E, and therefore E is equal to 2. Okay, well that fails because C and E cannot be the same. Okay, no problem. Let's keep trying. Let's try A equals 2 this time and C equals 1, see what happens. If that's the case, then it becomes 200 plus 100 plus 30 is equal to 290 plus 10E, and that's what, 330, so 40 is equal to 10E, and therefore E is equal to 4. Well, that works. Yeah, I think that all works. So in summary, we have A equals 2, B equals 3, C equals 1, D equals 5, and E equals 4. The circle shown has center 0, 0, radius 5. Two vertical chords are drawn at x equals minus 3 and x equals 3. Two horizontal chords are drawn at y equals minus 3 and y equals 3. What is the sum of the lengths of the four chords? Okay. Interesting. Well, I'm going to concentrate just on this part here. You see that? And that is half a chord. So half a chord, correct? Yeah. So the four chords, since they're all the same, the four chords, if let's just say half a chord, whatever the value is n, if I calculate that distance to be n, the answer would be the sum of the lengths, which would be 1, 2, 3, 4, 5, 6, 7, 8. So the answer would be 8n. Correct? Yeah. Okay, so I think I should be able to figure out that without too much problem. So let me draw a line from here to here, and that should be good enough. That triangle, and that of course is a right triangle. Okay, so this base I believe is 3, right? They even tell you that this is x equals 3 somewhere, yeah, here. And then the radius they tell you is 5. Okay, great. So that can easily be figured out. So 3 squared, some of you already know the answer because it's one of the most famous Pythagorean triples. It's just 4. So therefore 8n would be 8 times 4, which is 32. A bag contains 8 chips, each labeled with a different prime number, greater than 1 and less than 20. 2 different chips are selected from the bag at random, and their labels are multiplied. What is the probability that the units digit of the product is 9? Oh boy, so this is another one of those time-consuming ones. So here's the prime numbers, right, between 1 and 20. And what we're doing is we're taking 2 and we're multiplying them and seeing what the units digit is. So the probability would be something over something. This is our, of course, specific condition. Specific condition, which is explained in the question. And the denominator would be the total. Now the total is a little bit easier to figure out. You have, is it two different or can it be the same? Yeah, two different. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities for the first chip, and then we have to choose something different, so 7. But then we have to divide by 2 because, for example, if we choose 5 and 7, that's the same as 7 and 5. So this has to be divided by 2. Okay, now we just have to concentrate on the specific condition, which obviously is going to be much more time consuming. Okay, let's see. I'm trying to think if there's any way to do it without manually doing it. Yeah, looking at units, digits. Probably is, right? I'm just going to do it the long way, and then if you guys have a quicker way, then that's fine. I mean, obviously, the quicker way is the preferred way in math contests because you have such limited time, but for the sake of completion, I'll do it the full way. So the first thing I'm going to do is look at 2. 2 times 3, 2 times 5, 2 times 7, and so on. And then we'll see what is the units digit. 2 times 19. Okay, so here we go. So this is 6, 10, 14, 22, 26, 34, and 38. So none of these have 9 as a units digit. Okay, so far we have none. Let's move forward. 3 times 5, 3 times 7, 3 times 11, 3 times 13, 3 times 17, and 3 times 19. Like that. Okay, so that's 15, 21, 33, 39, 51, and 57. Okay, so we got one. So far, so good. We have one product that has a units digit that is 9. Okay, so I think we're on the right track here. It's just, as I said, time consuming. 5 times 7, 5 times 11, 5 times 13, 5 times 17, 5 times 19. All right, let's see. 35. Oh, these are all 5s. 55, yeah. So none of these are going to fit our criteria. Okay, no problem. Let's just keep moving forward. 7. The good news is that with each number, we're getting less calculations. That makes our life easier. 77, 91, 119, and 133. So there we go. We have another one. And I think we're almost done. We're coming closer to the end. 11 times 13, 11 times 17, 11 times 19. 143, 167, and 209. And that is a third one. And then I think we just have 13 times 17, 13 times 19. And that's 221, 247. And finally, 17 times 19, which is 323. So we only have 3. 1, 2, 3. 1, 2, 3. So 3 is what goes on the numerator. So the actual number would be 3 over 28 is the probability. What is the smallest 5-digit positive integer with the property that the sum of its digits is 1 less than the product of its digits? So we have A, B, C, D, E, some 5-digit number, and then they're saying the sum of the digits, A plus B plus D plus E, is equal to the product, but there's a little bit of a difference here. 1 less, right? So 1 less than the product. So the sum of the digits, let's say the sum of the digits was 20, and the product of the digits is 21. Okay, I got it. So we just have to add a 1 here. Oh, okay, so how do I do this? So I think this is just trial and error. I don't think we're going to expand this because that would be crazy. And we're looking at the smallest. Okay, so that helps. I'm trying to see if I can get the smallest. How about if it's all 1s? That's the smallest possible number I can make, right? 5 digits positive integer. Could it be zeros? I don't think so, because if it was zeros, then this would be, if any of the digits was 0, that would be 0, the product. And then the sum would never be equal because you're adding this 1 here. Yeah. Okay, so there can't be any zeros. I'm pretty confident about that. Okay, so let's go with 1s. If it's 1s, then this would be 6, this part here, and this would be 1. Okay, so that fails. How about if there's all 1s and then we have one digit that's not a 1? Then that would be 5 plus E, and then that would equal E. And that doesn't work either, because that would mean 5 would equal 0, and that obviously doesn't make any sense. How about if you have 3 and then we have 2 letters that are not 1? That would be 4 plus D plus E is equal to D times E. Okay, this looks promising. Let's see here. If I put, trying to think of, it's probably even. It's probably even on both sides since we have this 4. Not necessarily, but how about if we have 2 and 6? Then this would be 4 plus 2 plus 6. And this would be 2 times 6. So that's 12 and 12. Aha, got it. All right, so that means that this works with D and E being 6. So the number is 1, 1, 1, 2, 6. Now, the key thing is that they want the smallest, because I'm sure there's other numbers that would work, but this is the smallest one. At some time in the afternoon, Joni set 3 clocks to the correct time. Clock A is accurate, clock F is fast, clock S is slow. After 60 minutes had elapsed on clock A, S showed that 54 minutes had elapsed, and F showed 64 minutes had elapsed. At some point later that same afternoon, clock S read 7:20, F read 8:10. At what time did Joni set the 3 clocks to the correct time? So we have A, F, and S, right? So we have 60 minutes elapsed. This will be 64, and this will be 54. So this is a this is a plus 4, and this is a minus 6 type situation. Let me just draw some lines here. So the difference between F and S is 10. So the difference. And that's all they give us, really. That's not much. I'm assuming that that's the sort of the general pattern, meaning every 60 minutes, if you have another 60 minutes, you'll have another 4-minute delay, and another, meaning it'll be fast by 4 minutes, slow by 6 minutes. So then this becomes 20, the difference, overall total, because this would be up to whatever, 128, I think, right? Then that would be 108, and that's a difference. Yeah, it'd be 128, and this would be 108, and the difference between 128 and 108 is 20. So then eventually they get to F is 8:10, 8 hours, 8:10, and this is 7:20. So this difference is 50. Okay. So that's nice. So this was 30. There's a 30 and a 40. So there was plus 60, and then plus 60. I got it. Okay, so 5 times that this has happened. Okay. So, okay, I got it. So this was plus 4, this was plus 4, this was plus 4. Yeah. So a total of 4 times 5, so plus 20. Plus 20. So this time, the time here would be 750, right? Because this accounts for plus 20, so this plus 20 is why you get 8:10. And what they're asking for is what time did she set the clocks initially? Meaning, what is the time up here? Well, that's exactly 60 times 5 before, so exactly 5 hours before, so that would be 2:50. 2:50 p.m. I believe. Yeah. 2:50 p.m. is the answer. In a sequence of 7 numbers, each number after the first 2 is the sum of the previous numbers. If the 7th number in the sequence is 97 and the sum of the 7 numbers in the sequence is 245, what is the third number in the sequence? So we have these numbers. There's 7, right? Okay. So we have an A, then a B, then an A plus B, then A plus 2B, just following what the question tells me. 2A plus 3B, 3A plus 5B, and then finally 5A plus 8B. You got it? Okay, so then 5A plus 8B, that's 97 according to the question. So I'm going to put that as equation 1. And then 13A, wait, hold on here. What did they say? Oh, yeah, the sum. Yeah, the 13, I was right. The sum of all 7 numbers. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 13A, which is what I initially said, plus 20B is 245. Okay, so that's fairly straightforward system of equations. I just have to solve those. So however you want to do it, I think I'm going to do 5 times equation 1 minus 2 times equation 2. That'll do it. That'll give me 25A plus 40B minus 26A minus 40B. Already something cancels. 5 times 97 minus 2 times 245. So this basically gives me minus A is equal to minus 5. A is therefore 5. Plug that back into any of these. And when you do, you get 5 times 5 plus 8B is equal to 97. Solving that, you'll get B is equal to 9. And therefore, what did they want? Let's see here. What is the third number? This is the third number. So third number is A plus B. A is 5. B is 9. That should be B. And that is 14. If f at x is equal to x squared plus 9x minus n for some positive integer n, f at n is equal to minus 16, what is the value of f at minus 2? Okay. Well, let's see here. First, let's calculate that f at minus 2. So that will be minus 2 squared plus 9 times minus 2 minus n. So that's 4 minus 18 minus n. And that's minus 14 minus n. Okay. Whatever that means. I'm not sure if that helps. And then what do they want us to figure out? Oh, I got it. The actual numerical value. Oh, so that means we would eventually need to figure out n. Okay. So how do I do that? I think we use this here. So f at n, using this, is n squared plus 9n minus n. And they're saying that's minus 16. Okay, so minus 16 is equal to n squared plus 8n. Okay, so then we just have to solve this. That shouldn't be hard. So that factors beautifully, right? N plus 4 squared, so n is equal to 4. Minus 4, sorry, minus 4. So then we go back here and just plug it in. Minus 14 minus minus 4, and that's minus 10. Four dice each have the following 3 properties. The number of dots on each face is an integer from 1 to 6. No 2 faces on the same die have the same number of dots. Each pair of faces on opposite sides of the same die have a total of 7 dots. The dice are arranged as shown below so that each pair of faces from different dice that are touching have a total of 8 dots on them. And 5 of the visible faces, including the one labeled X, have had all of their dots hidden. What is the number of dots on the face labeled by X? All right, so it's a little game here. So let's see if I can do this. So there's really just 2 things that we will work with. The first is that each pair of dice sorry, if you have a dice, each pair of faces on opposite sides have a total of 7. So for example, if you have a dice, right? Here's a dice, and this is a 5, and I ask you the opposite face, what is the number? Well, since the total is 7, the opposite face, which you can't see, would be 2. I'll just write it, outside. You got it? And then the other piece of information is this one, that if you have another dice attached, like that, and 2 faces are touching like this guy, there's going to be 2 faces touching, one on dice number 1 and one on dice number 2. Those 2 faces, if added together, have a total of 8. So for example, if one of those faces was, let's say 3, the other face has to be a 5. Got it? Okay, so here we go. Let's see what I can do. So this top is 5, so that means the bottom has to be 2. I'll just put it there. This is that you can see is a 3, so the other side has to be a 4. I'll just put that there. And that the only thing that is left for us is 1 and a 6. Now, I don't know which, does the 1 go here, or does the 1 go there? But here's the thing. This part is going to have 2 sides touching, and they have to total 8. So if I put a 1 there, the other one would have to be a 7, and that's not possible because they only go from 1 to 6. So that means that the 1 is on this side and the 6 is on this side. I'll just put it there. Got it? Okay. So then now we turn our attention to the middle dice. This has to be a 2 because remember, the touching faces have to add up to 8, and 6 plus 2 is 8. Okay. Then what? Then we have a whole bunch of choices here. Okay, well, what do we have? 1 is not going to go here, this side, this right here, because remember the same problem. If we put a 1, then the other one would have to be 7, and that's not possible because they only have numbers 1 through 6. So it's not going to be a 1. 2 and 6 are already gone. So it can't be a 1, 2, and 6. We only have 3, 4, or 5 as our options. Okay. I forgot the most obvious thing. They already told me this rule right here. Each pair of opposite faces has to be 7. So if that's 2, this is a 5. I'm overthinking here. Okay, well that makes it very helpful. Then that means that this guy, if you look at that, side, which I cannot show you, not the top. The top is 6, but I'm talking the other side of on the other dice. Since those opposite faces have to add up to 8, that has to be a 3. Got it? And then this face right here, that and the 3 have to add up to 7, so that has to be a 4. Okay, great. And then since the top face is 6, the bottom face is a 1, and then the only numbers I have left for that die are 2 and 5, correct? Yeah, 2 and 5. So then I have to figure out where does the 2 go and where does the 5 go. Well, to get a little bit of help, I'm going to look at the last die, the one that has a 4 on the top. If the 4 is on the top, then that means a 3 is on the bottom. If a 3 is on the bottom, then that means the 3 and the 4 have already been taken. Got it? So that will help me figure out if therefore that connection, that will allow me, if I put a 2 out here, then a 5 goes there on this side, and that would mean on the last die it would have to be a 3. But that's not possible because the 3 has already been covered. So this is not going to be a 2, this is going to be a 5. Yeah, the side that you can't see. And therefore this would be a 2 right here. The side that would be there. And then on the other dice it would be a 6. And then therefore this X would be 1 because 6 plus 1 is 7. There we go. So it took a little bit of thinking. It was actually not so bad as long as you just follow this rule and this rule right here. Those are the only 2 rules you need. x equals 1. For positive integer n, the Anderson number of n is the integer obtained by writing the integers from 1 through n in the order. For example, the Anderson number of 19 is as follows. What is the smallest 4-digit integer n for which the Anderson number of n is divisible by by 9? So 4-digit. So 1, 2, 3, 4. So it's 4 digits. So then they want the smallest. So what's the smallest 4-digit number? It's 1000, right? And then the largest would be 9999, like that. So, okay. So hopefully we'll get the answer sooner rather than later. Meaning, if we test out 1000 and then test out 1001, like that, hopefully we'll get it soon. Okay, so the first thing we need to do is add up the numbers, the digits, I should say. So, for example, if we, starting with, the very beginning, all the way up to, we get to 1000, but before we get to 1000. So these are all the numbers from 0 to 999 before we get to that first 4-digit number. And let me think about this. So, I forgot the divisibility rule. That needs to be talked about before we even proceed. If a number is divisible by 9, then that means that the sum of the digits of n is divisible by 9. That's one of the many divisibility rules. So, for example, what's an example? 81, right? 81 is divisible by 9, but so is the sum of the digits, which is 8 plus 1, which is 9, which is obviously divisible by 9. So that's what this means. Okay, so now we can proceed. So if we look at this right here, we have 1000 of those, and each has 3 digits. So we have 3000 digits. Correct? And hopefully you can observe, although this is not entirely obvious, that each digit, 0 through 9, occurs the same number of times. So that means the 0 occurs 300 times, the 1 occurs 300 times, all the way down to the 9 occurs 300 times. So if we were to add up the sum, it would just be 300 times 0 plus 300 times 1 plus 300 times 2, and then all the way till 300 times 9. And that you can easily get as a sum, 3,500. Okay, so if we add up all the numbers from 1 till 999, we get that. Now if I said to you, what if I have the sum of the first 1,000, meaning going up to 1,000? Well, then all you have to do is just add the sum of the digits of 1,000 to this number, and that is really just adding 1. So if I made a little table here, if you have n, you have sum of digits. So we had initially 999, and we got sum of the digits to be 13,500. But if I have 1,000, then you're just going to add 1 plus 0 plus 0 plus 0 to this number. That just brings it up by 1. And then we have to say, is this divisible by 9 with a question mark? And the answer here is no. So okay, keep going. So 1001. Now the sum of the digits is 13503 because you're adding another 2. And again, no. And I keep going here. So 1002, 13506, 1003, 13510, 1004. I'll tell you which one is divisible by 9 once I see it. 1005, 13, 521, Yeah, because you're adding 6, right? 1006, you're adding 7, so 13528, 1007, 13536. This is divisible by 9. Yeah. So the smallest number that qualifies would be 1007. Given a positive integer with at least 2 digits, a new integer can be obtained by removing its lead digit. For example, the leading digit can be removed from 589 to get the integer 89. What is the smallest positive integer n with the property that n is 57 times the integer removed by removing its lead digit? So then they don't tell me how many digits this n will have. Does it have 2 digits, 3 digits, 4 digits? Yeah. Okay, so I guess I just have to do it one at a time. Let's say it has 2 digits, so then it's AB. And if you remove the lead digit, it becomes B. And then they're saying that this is 57 times that, right? Is that right? Yeah. So if you expand this, it's 10A plus B is 57B. Therefore, 10A is equal to 56B. And since A and B are digits, I don't think this works. Because this side is always going to be divisible by 10, and this side is not divisible by 10. And B is a digit from 0 to 9, so that fails. So it obviously can't be a 2-digit number. So let's try a 3-digit number. Hopefully it'll be 3 digits. So that'll be ABC. And then if we drop the A, it'll be BC, and then it's going to be times 57. Yeah. Okay, expanding this, so this is 100A plus 10B plus C is 57 times 10B plus C. All right, let's see what we get. We have 100A plus 10B plus C is 570B plus 57C. 100A is equal to 560B plus 56C. Okay. Now I think we have to do trial and error, because I don't know how else to do this. Okay, well, concentrate on the C. C is between 0 and 9, right? Now keep in mind this side is a multiple of 100, so this side also has to be a multiple of 100. Now how can we do that? We have to choose C carefully. I think the only one that would give us a multiple of, well, if it was 10, but we can't choose 10 because we have to choose between 0 and 9. How about if we chose 5? 5 would do something. It would make it 280. At least we have a 0 in there. Because I think that's the only one that gives me a leading a units digit of 0. 56 times 5 is 280. And then if we divide through by 10, we get 10A is equal to 56B plus 28. And so somehow I have to get this side to be a multiple of 10. Can I do that? I don't think so. Because the only one I can think of is B. If B is 2, then that would be 112, that would be 140. And then 10A, and then A would have to therefore equal 14, and that's not possible because A has to be between 0 and 9. Oh, that falls apart. Oh boy, so it's got to be a 4-digit. Yeah, so just time consuming at this point, just draining our valuable clock that we have on a math contest. All right, so I wish they had told us. It'd be nice in the question, what is the smallest 4-digit positive integer right here? If they had put 4-digit, yeah, right in there, right in here, that would save us all this. But okay, well, that's life. So let's go 4 digits, 1000A plus 100B. And I don't even know if it's 4 digits. If it's not 4 digits, then I give up. All right, so then this is 57 times 100B plus 10C plus D. Okay. Collecting like terms, 1000A plus, well, this side I don't think does anything for now. 5700B plus 570C plus 57D, right? 1000A is equal to 5600B plus 560C plus 56D. Got it? And I guess at this point, again, trial and error. So this side is obviously a multiple of 1,000. So and this is already a multiple of 1,000. So we have to sort of make this a multiple of 1,000. Let's see here. If I chose C to be 2, that would be 1120. And then I think we had a 280 in there somewhere. We had a 280 there. That'll work actually. If I put 280, that means D is 5. So 1120 plus 280 is 1400. Wait, is it? Yeah, 1400. 1400. 1400. If this is 1, then that's 5600. So 5600 plus 1400 is 7000. Oh, that's great. That works. That means A is 7. Okay, so let me regroup here. A is 7, B is 1, C is 2, D is 5. So the number A, B, C, D is 7125. All right. There you go. Some devices display digits using an arrangement of segments. For example, the digit 8 uses 7 segments. How many integers from 100 to 999 inclusive can be displayed using exactly 17 segments? Okay. Well, let's see here. Let's make a list. So this is the digits, obviously. And then let's make a list of the segments. So, 1, 2, 3. So this is 6 segments. 2, 5, 1, 2, 3, 4, 5, 4, 5, 6, 3, 7, and 6. Okay. And we want the magic number is 17. Okay. So let's see here. Oh boy, there's another one of those time-consuming ones. I think everything on here is time-consuming today. Okay, so let's just figure this out. Digits and segments. If we want a number that has 17 segments, we have some possibilities, right? So let's start with the biggest one. The biggest one is 7. And that's the digit 8. And if you use it, let me think about this. If we use it twice, if we use it twice, then the next one, that would be 7 and 7, so that's 14. You would need, therefore, 3. A number that uses only 3 digits. Sorry, 3 segments. 3 segments. Sorry, already getting confused. So that would be the digit 7. And that's one way. But what's interesting is that this number can be written like it has 3 iterations. You see what I mean? These 3 guys. So that's a total of 3 numbers. So this is how we're going to approach this. We're going to just sort of painstakingly go through this process. Again, digits, segments. So if we have an 8, we already exhausted the 8s. So meaning 2 8s. If we have just 1 8, then we have we've already used 7 segments, so we have 10 segments left. So we can use 6 4, we can do 5 5. So let me use the 6 4 first, and then we'll see. 6 and 4, we got several choices here. 6 and 4, oh boy. We have 0 and 4, right? And this is going to give me 6 possibilities, right? 8 0 4. 8 4 0 4 0 4 8 0 4 0 8 and 0 4 8 and 0 8 4. Oh, these 2 cannot count. So I'm down to 4 because it has to be 3 digits, right? Yeah, it has to be between 100 and 999. Ooh, that makes it a little bit tricky. But I think it's only tricky if there's a 0 involved. So everything else should be fine. Okay, let's just keep going here. Digits and segments. So 8, 7 segments. How about... it'd be nice if I kept that in there. It's nice to keep that in there. How about 6 and 4? And that would give me 6 segments and 4 segments. And again, this one will give me another 6. Yeah. So 8, 6, 4, and now all of its iterations. And what are we doing here? Same kind of thing. We're still sticking with the 8s here. Do we have any other? We had 0, 6, and 4, right? Which we'll use 0 and 4. 6 and 4. And 9 and 4. 9 and 4, that'll do it. That'll be 6 and 4. And then 8, 9, 4, and its iterations, so that's another 6. Okay, so far so good. I think we've exhausted the 6, 4, this guy, this type of scenario. So now we got to move on to keeping the 8s, the 5, 5 scenario, 5 segment, 5 segment, and we got a whole bunch of those. We actually have quite a few of those actually. We have the situation where you use the same digit twice, and that would give me 3, right? 8, 2, 2, 2, 8, 2, and 2, 2, 8. And then similarly, if we had 8, 2, 8, 5, 5, that's getting, in terms of digits and segments, yeah, that gives me another 3. And then if I use 8, what is 3 here? 3 is 5 also, right? So 8, 3, 3. Yeah, 8, 3, 3. That's another 3. And then we have a whole bunch of ones where you have 8, but then you have different numbers. So 8, 2, 3. That'll give me 6. And that is 7, 5, 5 for the segments. And then if we have 8, 8, 2, 5, that's 7, 5, 5. That gives me another 6. And then if we have 8, 3, 5, that gives me also 6. Okay, I think that is the first batch. That's a pretty good list here. So let me add this up. So you have this 3, and then we have 6, 6, 6. That's 12. Sorry, 18. Then 21, 24, 27, 33, 39, and 43. So, and then 3, so we're up to 46. Yeah, so all these guys, 46. Okay, so let's see if I can come up with another. Let me put that 46 up here actually. I'm going to need the space. Okay, so now we have to keep going here. And I think so far you get pretty much a pretty good handle on this question. So it shouldn't be too bad. Let's just continue with the digits and the segments. Now we're moving on, and we're moving on to a different type of a 665 scenario. 665, I think, will give us the remaining, and an example of that would be, let's see here, an example of that would be 0, 0, 2. Yeah, but the problem you'll see with these is that there's a lot of ones that we have to eliminate. Yeah, because this number itself, 002, is invalid because it's not between that range. Okay, So let's just concentrate on the 665, and then we can eliminate the ones that are not in the range. Okay, for 665, the possibilities for this guy, how many digits have 6 segments? 0, 6, and 9. So 3 possibilities. And then similarly, same thing, 3. And then how many digits have 5 segments? 1, 2, 3. 3, correct? Okay. So there's 27 possible ways of getting 665. But there's 3 iterations of this guy. It's 665, a 6 segment, a 6 segment, a 5 segment, or you can have a 656. These are segments, not the actual digits, or a 566. So there's 3 of these guys. So this 27 has to be then multiplied by 3. So you get 81. So there's 81 possible additional numbers. But we have to subtract from that 81 the numbers that are not in the range. Where is it? 100 to 999. So basically, it'll be a whole bunch of, and I'll let you count those. It'll be the first one I gave you right up here, and there's a few others, right? There's 003. There would be a 005 ... all the way down to 095, 065, and so on. And there's going to be 18 of those guys. So you take that 81 and you subtract from it 18, and you get 63. So then you have to take this guy that we calculated earlier and to get the grand total. So 46 plus 63, and that is 109. That is the final answer. In the diagram, OPQ is a quarter circle of radius 1. Square OABC is inscribed in OPQ so that A is on the line segment OP, B is on arc PQ, and C is on line segment OQ. Another circle arc is drawn from A to C with central O, and the region bound by this arc, AB and BC, is shaded. Inside the quarter circle OAC, this process can be repeated to inscribe a square, then draw a circular arc to obtain a smaller shaded region. If this process is continued indefinitely, what is the total area of the infinitely many shaded regions? So that number there makes me think of an infinite series. Infinite series. Let's see if I'm right. I'll get an understanding once I figure out the first 2 or 3. If it is an infinite series, then I can just add them all up. You guys remember, right? If you have the sum of an infinite series, so is given by S is equal to A over 1 minus R, where A is the first term and R is the common ratio. So let's see. I'm pretty confident it'll be that way, but I'm not 100% sure. We'll find out. Okay, so since they already gave us this nice diagram, I don't want to redraw it, but hopefully I won't have to label it too much because otherwise it'll get confusing. But the first thing I want to do is draw a line to kind of represent, from there to there. That should be sufficient. That line is important, and I'll explain why. That initially represents the radius of that big quarter circle, right? So we are told actually that OQ is 1. So that means OB is 1 also, right? Because it's a radius. So then what I'll do is I'll draw it on the side. I don't want to draw it on the diagram because it'll just mess it all up. It'll be way too confusing. So that square that initially was A, B, C, and O, that OB is 1. So I want actually the sides B, C, and OC. Well, that can be figured out with Pythagoras fairly easily, right? So we have x squared plus x squared is 1. 2x squared is 1. X squared is a half. And therefore x is 1 over root 2. Okay, that helps me figure out the first shaded region, and I'll just call it region 1, that first, and then as you can see, they've drawn other. This is region 2, this is region 3, and then 4 and 5, and so on. I think the first 3 should be sufficient for me to assess if this is indeed an infinite series with a common ratio. Okay, so let's turn our attention to figuring out 1. 1 is fairly simple. It's just the area of the square, which would be 1 over root 2 squared, minus the area of a quarter circle. So the quarter circle, where that guy with AC is the arc. So that's going to be pi r squared all over 4, because it's a quarter circle, so I have to divide by 4. Now, what is r in this case? R is the radius of that quarter circle, right? And the radius of that quarter circle would be the distance from O to here, and that's the same as the distance from O to C. Yeah, and O to C we just figured out was 1 over root 2. Okay, so that makes my life easy. So that's a half minus a half pi over 1 over 4. So that's a half minus pi over 8. And then therefore it would be 4 minus pi over 8. Okay, now, so far I can't tell you if this is an infinite series because I'm going to need at least a couple more. No problem, let's turn our attention to the next guy. So that was 1. Now we're turning our attention to 2, this region. Very similar process. Again, draw a little square. And this time, same thing. We want to figure out the sides of that square. Well, we know the diagonal is equal to OC. OC. And OC we figured out in the previous question was 1 over root 2. So this diagonal is 1 over root 2. And then we can figure out the sides. Very similar. Y squared, 2y squared is equal to 1 over root 2 all squared. So that means we have 2y squared is equal to 1 half. Y squared is equal to a quarter, so y is a half. Okay, so y is a half, and what does y represent? It represents the sides of that square. So let me just, on the diagram itself, draw this square here. Yeah, that square. Okay, so there we go. Now we can figure out 2. That shaded region. The shaded region is going to be the area of the square, which would be 1 half squared, minus pi r squared over 4. Now what's r in this case? R is the distance from the O to here, right? And that is the same as the side of the square, which we just figured out to be a half. So there we go. So this is a quarter minus, it would be 1/4 times a quarter, pi over 16. So 1/4 minus is 4 minus pi over 16. And this was 4 minus pi over 8. Okay, looks very promising. But I'm going to do one more just to be sure. Just one more, and that would be this 3 here. Yeah, that 3. Okay, so same thing. Let's draw a square. And this time, let me use a different color. The square we're concentrating on is this guy. And the diagonal we figured out earlier was, where was it? Here, half. So that's a half, and then we can call this z. And then again, 2z squared would be a half squared. Correct? So 2z, so z squared is 1/8, and then z is 1 over root 8. So 3, that shaded region that I've called 3, would be 1 over root 8 squared minus pi r squared, which would be 1 over root 8 squared over 4. So that looks to me like 1 over 8 minus pi over 32. And then that looks to me like 4 minus pi over 32. All right. So I'm convinced now. So we have the following. Our sum is 4 minus pi over 8 plus 4 minus pi over 16 plus 4 minus pi over 32 plus dot dot dot. So it is indeed an infinite series or infinite sequence. I think series is probably the better word. And then first term A is 4 minus pi over 8. The common ratio R is a half. Now, if you're wondering how I figured that out, you can just take the second term and divide it by the first term. That's how to figure out the common ratio. And if you do this, of course, this will be a half. So there we go. Just use our beautiful formula here. S would be A, which is 4 minus pi over 8 over 1 minus R, which is a half. So this is 4 minus pi over 8 over a half. And therefore, this would be 4 minus pi over 8 invert and multiply. And that would give me 4 minus pi over 4. 4 minus pi over 4 is the answer. The two angles x and y, both between 0 and 90, satisfy both of these equations. What is the exact value of sine x plus sine y? Well, let's see here. You guys remember that famous trig identity, sine x squared plus cos x squared is 1. That's the one that is probably the most well known. I'm just trying to think what's the right approach here. Well, let's see. Let's just add them and see what happens. So if I add both of those equations, I get sine squared x plus cos squared x, purposely grouping those together, plus cos squared y minus sine squared y. And that's going to be 89 plus 71 is 160 over 144. Okay, so this one is 1, so that's really nice. And this one, I guess I could factor it. I'm not sure if it helps to factor it, but let's just see. Cos y, sine y, plus and minus. And they want this guy, so we don't have that yet, but hopefully we'll get there. Okay, so that's what I have so far. And if I put this on the other side, it'll be 16 over 144, which reduces to 16 over 1. Yeah, I get this is 1 over 9. Yeah, 1 over 9. Okay. Does that help at all? Or does, I guess what I'm asking is, does factoring it help? I don't think so. I'll just leave it like that, actually. Let me just leave it as cos squared y. Remove that, minus sine squared y. I was hoping that it would help, but it's okay. All right, so let me go back to that famous identity. And cos squared y would therefore be 1 minus sine squared y. Okay, that's really good. And I can substitute that in. 1 minus sine squared y minus sine squared y. Oh, that's really good, because now I have just one variable. So this will be 2 sine squared y, 1 minus 1, 8 over 9. Yeah, 8 over 9. And therefore sine squared y is 4 over 9. And then sine of y is 2 over 3. Okay, that's good. I got 1/2. Look, if you could look up here, I've got the sine y already. Okay, now I guess I just have to find sine of x. So how do I do that? I think I just go right back to the same equation, right? Is there some equation? Hold on. Which equation? Oh, yeah, one of these guys up here. I scrolled it down. I couldn't remember them. Okay, so which one do I want to go back to? The one that, well, I need an x, sine x, so I need cos x. So I think I'll go with this one here. Yeah, that one. And yeah, I'll try to keep it in the same screen here. Should be okay. Okay, so cos of x squared minus sine of y squared. Well, this is sine of y, so sine of y squared would be, well, I actually already have it, 4 over 9. And 71 over 144. Okay, this looks very promising. So cos of x squared is going to be 135 over 144. And then if I take the square root, it'll be the square root of 135 over 12. Right? Now, I don't need cos x, I need sine x, as you can see here. So that shouldn't be a problem. Just make a little triangle. And x adjacent over hypotenuse. So this is 135 over 12. Using Pythagoras, you can easily figure out the other side to be 3. Right? 9 plus, yeah. So therefore, the sine of x is 3 over 12, which is 1/4. And there we go, we got it. So sine of x plus the sine of y is basically 1/4 plus, we had it over here, 2/3, right? Yeah. So then adding these, 1/4 plus 2/3 is 11 over 12. In the diagram, triangle ABC is right-angled at B. Point D is on BC, so that BD is equal to 4, CD is equal to 5, and cos of CAD is 12 over 13. What is the length of AB? Okay, so this to me screams cosine law. Yeah, I can immediately tell this is cosine law. And for those of you who don't remember, no problem. I'll just kind of give you a brief. If you have a triangle, that's theta, that's A, that's B, that's C. Cosine law states that C squared is equal to A squared plus B squared minus 2AB cos theta. Okay, so we're going to use the same on here, and let's see what we can get here. So CD squared would be AD squared. First of all, I need to identify which triangle I'm using here. I'm using ACD, so triangle ACD. So it would be CD squared is equal to AD squared plus AC squared minus 2AD AC cos CAD times cos CAD. Okay, so let's plug this in. So we got 5 squared, and instead of the ADs, I'm going to add variables if it's okay. Just going to call that X, and I'm going to call this Y. It just makes it easier. And then we'll substitute it back at the end. X squared plus Y squared minus 2XY. And this cos CAD, they very, very nicely gave us 12 over 13. Okay, so let's see what we get. So this is, not as, well, we still got, interesting here. I have to make some substitutions because this has too many variables. It has 2 variables I was hoping to solve, but I can't. Okay, so that's where Pythagoras comes in. That's why they gave us this right angle. Let's call this z. So z squared plus 4 squared is x squared. And then z squared plus 9 squared is y squared. So this is all going to be changed in terms of z's here. Because so the z squared is x squared minus 16. And z squared is y squared minus 81. Okay, so this is 25. And then x squared is z squared plus 16. And then the y squared is z squared plus 81. And then this minus 2, this guy, minus 2xy, x is the square root of z squared plus 16, and y is the square root of z squared plus 81. Correct? Okay. All right. That hopefully, although it's messy, it's not as clean as I'd hoped. A lot of algebra here, but hopefully that we can solve it at least. Okay, so put everything on one side, and when we do that, we get 24 over 13 z squared plus 16 z squared plus 81, all under the square root sign. And on this side, we get 2z squared plus 72. And then, what do I do now? Clean it up a bit, and then just leave this whole radical by itself. And then we'll have to square both sides. Oh boy, that gets really messy, right? And then when we do, divide through by 2, all that stuff. And then we'll get z squared plus 36 over 13 over 12. Yeah. And then square both sides. And then when you do, the radicals will disappear. The one radical sign. And this becomes z squared plus 36 squared. And then this becomes 169 over 144. Got it. And then, if you want, you can let z squared equal a just to make it cleaner. A plus 16, a plus 81, correct? And then this will be a plus 36, all squared, 169 over 144. And this is what you have to solve. And this isn't so bad. It's not as that this unfortunately makes it a mess in terms of the numbers, but you can expand and, collect like terms, and I'll let you do that. Yeah, I'll let you do that. I'm sure you can. It's just a quadratic. It's just the numbers are not as nice. And when you do, you get a equals 36. So that's the good news. And then since z squared is equal to 36, z is equal to 6. And z is what I had given to AB, as you can see from the diagram. So AB is equal to 6, and that is the answer to the question. The positive real numbers x and y satisfy both of these equations. What is the value of x plus y? So as always, log rules come into play, and I think the immediate log rule I'm thinking of is the log of x to the base y is equal to 1 over the log of y to the base x. That one. Okay, so if I let log of x to the base y equal a, then the log of y to the base x would be equal to 1 over a. So therefore, this equation, the second one, this one, becomes 3 a plus 3 over a is equal to 10. And if you multiply through by a, you get 3a squared plus 3 is equal to 10a. And then 3a squared minus 10a plus 3 is 0. And this factors very nicely, fortunately. So 3a, a, 1, 3, minus, minus. So a is equal to 3 or 1/3. All right, perfect. So now what? What are we trying to do? X plus, so we have to figure out what the values of x and y. Okay. So I guess this equation now is what we turn our attention to. And also keeping in mind these substitutions. So the log of x to the base y was 3, correct? So that means y to the power of 3 is x. Or you can use this guy, that the log of x to the base y is 1/3. So that means y to the power of 1/3 is x, or y is equal to x to the 1/3. Either way, I think you'll get the same answer because it says the value. Now you can verify, you can either use, where is it? This or you can use this. You can do both, and you'll see that the answer is the same. I'm just going to do one. Well, I can do both. It doesn't really matter. I mean, if you want me to do both, I can. So now let's turn our attention to that guy. XY is 144. Okay? So I'll do both. Okay, so first let's start with this one. So that would mean we have y to the third times y is 144. So y to the power 4 is 144. So y would be root 12. And therefore x would be 12 root 12. And therefore x plus y would be 13 root 12. Yeah. And then if you really want to, you can change that. What's root 12 as a mixed radical? It's 4 times 3, so 2 root 3. So 2 root 3. And then that's 26 root 3. Right? So that's the answer. Now, if you want, I can do this same thing. It's exact same. So x times x to the power 3, 144. X to the power 4 is 144. X therefore would be root 12. Y is therefore going to be 12 root 12. And then x plus y would be 13 root 12. And as before, as a mixed radical, 26 root 3. Consider the polynomials f at x and g at x. There is an irrational number c such that f at c and g at c equal to 0. Given that p and q are rational, what are the three real numbers that satisfy x to the power of 3 minus 5x squared minus q is 0? So f at c and g at c are equal, and they're equal to 0. So let's plug that in. Here's the f at c formula, and here's the g at c formula. So we have c squared minus 2c minus p, right? And that is equal to c to the power of 3 minus 5c squared minus q. Substituting into there and there. Okay, so put everything, well, let's see here. Can I do anything here? I can put it all on one side, I guess. So, hold on, I'm trying to think, what am I supposed to do here? This, I probably should have done this separately. Let me do this separately. F at c equals 0. Yeah, and then that would make it c squared minus 2c minus p. And then to multiply through by c, I would get this. And that would probably be a little bit better since it has the same degree as g at c is 0. And g at c at 0 would be c to the power 3 minus 5c squared minus q equals 0. Okay. And then since this is 0 and this is 0, let's set those equal to each other. That would be a little bit better than this guy. Because that one just doesn't help at all, because then you got all this stuff. Okay, so if I set this guy and this guy to equal each other, that immediately I think will help. Let's just see here what happens. Yeah, because the c to the power of 3's cancel out. And then if I put everything on one side, I'll get 3c squared minus cp plus q is equal to 0. That is helpful. Yeah. And then, where is it? Over here, that guy, if I multiply that one by 3, it'll be 3c squared minus 6c minus 3p is equal to 0. Let's call this equation 1. Let's call this equation 2. And then I think at this point, if I did 2 minus 1, I could get something. And a few things would disappear. So 2 minus 1 would be minus 6c minus 3p plus cp minus q. And then therefore that would be, if I factor out a c, I'll get p minus 6 minus 3p minus q. And then let's put everything on one side. 3p minus q over p minus 6 is c. Okay, this is a very important point here, because they told us in the question that there's an irrational number c. Irrational. Now, if you remember, rational numbers are something that can be written, let's say you have a rational number, right? It can be written as, it could be written as a fraction, say a over b, where a and b are both rational. Now, they told us in the question that p and q are rational, right? So if p and q are rational, then if you look at the right side of this part, since p and q are rational, then if you use them in a fraction, that would be rational. But they're saying that that is irrational. So how can that work? It falls apart, right? The only way that it could work is if this denominator is 0. Now, that's the only way that c would be irrational. Okay, if that's the case, then that means p is 6. If p is 6, then we go right back to this guy, or this guy, whichever one you want to put it in, and solve for q. So that would mean minus 3 times 6 minus q is 0. So q is equal to minus 18. Yeah. And at this point, we can easily solve this equation since we have the value for q. So then we have x to the power of 3 minus 5x squared, and q, there we go. Let me just double check that. That was minus q, so it's minus 18. Okay, so then we just solve this. Factor this out, and then I think you're going to use a quadratic on this guy, and therefore x will be 3, and then the roots are going to be 1 plus or minus root 7 when you use a quadratic. So these are the 3 roots, if you remember what they're asking. In the diagram, you have a 12-sided polygon. What is the area of ADH divided by the area of the dodecagon? All right, so we need some lines. We need some lines to illustrate what needs to be done. Okay, so here we go. The first line I'm going to draw is, let's see, let me first think about this for a second. How about H till B? That's pretty decent. And then we can kind of just go from there. All right, and then the other line I drew, the other lines I should say, are from the center, which I'll call O, that guy right there, till A, till D, and that should help. So here we go. Now there's a formula that you guys may know, that if you have some sort of a triangle, and I say calculate the area, and you have a little bit of information, you have the angle, this angle there, and this side is A, this side is B, then the area of that triangle is 1/2 A times B sine theta. And that's what we're going to use throughout this question. So the first thing I want to do is figure out the total area. The total area of that entire 12-sided polygon that they're calling a dodecagon. So how do I do that? What I do is I break it up into its 12 components. Now I don't want to make the diagram too messy, but I guess I'll draw one more line to illustrate how you can break up that into 12 triangles. So I'll draw one line from O to I, or is that I? H-I, yeah. So like that. You got it? So if you take a look at the triangle that is OIH, right? That represents one of the 12 triangles that make up this shape, 12-sided shape. And then there'd be other ones. For example, if you drew a line from O to G, it would be OHG. That would be another triangle, and so on. There'll be 12 of them. And each of them can be calculated in the area by using that formula. Now the side OI, the side O till I or O to H. We don't know, so I'm just going to call it R. R for radius. So it would be 1/2, let's say OI times OH, and then this angle. So sine of theta. Let's put that theta in there. Okay, now the sides I don't know, so I'm just going to call them R. So it'll be 1/2 R times R. But the angle I can figure out. That's fairly straightforward. All the way around is 360, right? And then how many of those triangles do we have? We have 12 of them. So there's 12 of those thetas. So each of those thetas is 360 over 12, which is 30 degrees. So that angle we can figure out. So this is basically, and what's the sine of theta? Sorry. What's the sine of theta? I don't know. What's the sine of 30? The sine of 30, if I remember. Oh boy. Half. All right, so this will be 1/2 times r squared times 1/2. So it'll be 1/4 r squared. Correct? Yeah. But this was just one triangle. I think this was representing triangle, what was it? OIH. OIH equals. But we want the whole thing. So the whole thing, total area, would be 12 times that. So 12 times 1/4 r squared, and therefore that's 3r squared. So that is very important. So that's the first step. Okay, moving right along. Now we have to figure out the area of that shape that they're calling triangle ADH, right? Let me just double check here. Yeah, ADH. Antidiuretic hormone, if those of you know what that means. Okay, so how do we do that? Well, same way, same formula right here, but it may not, this guy, but it may not be as obvious. So we're going to break it up into 3 triangles. Triangle ADO, triangle, let's see what else, AOH, and triangle ODH. So all we did was just take that triangle, break it up into 3, and that's what those lines were drawn by me initially to help you see that those 3 triangles exist. And then you just apply this formula 3 times. So this will be 1/2 ADO would be R times R. Aha, we have to figure out the angles. ADO. Okay, so ADO, we've got to figure out this angle. That angle would be 30 times 3, right? Because it involves 3 of those smaller triangles. Yeah. So that would be 30 times 3. Okay. AOH, again, R times R, and then AOH. Okay, so 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 times 30 for the angle. And then finally the ODH, that's going to be 1, 2, 3, 4. 4 times 30. All right, I'm pretty confident that's going to be the case. So it's going to be, well, the 1/2 r squared we can factor out. Oh, sorry, I forgot to put the signs in there. Sorry about that. We got to put the signs. Okay, so it's going to be the sine of 90 plus the sine of 150 plus the sine of 120. Okay, so 1/2 r squared. And then it's 1 plus 1/2 plus root 3 over 2. So this is a 1/2 r squared, 3 plus root 3 over 2. Yeah. Okay, so finally, now we have the ratio. So we got the ratio, this over this. So we have 3, this, I got to do it the right way here. ADH, the triangle ADH over the total. That's what we're doing. Okay, so that's 3 plus root 3 over 4 r squared over 3 r squared. Well, the r squared's canceled. That's wonderful. So then that's just going to be 3 plus root 3 over 12. And there you go. That is 3 plus root 3 over 12 is the final answer. The regular pyramid EABCD has square base ABCD and a volume of 28. The points P and Q are on EC and ED respectively, such that EP over EC is 1/3 and EQ over ED is a half. Figure EABPQ has 6 faces, 2 of which are triangle APB and triangle AQP. What is the volume of EABPQ? Well, a lot to unpack here, so let me just summarize. So first thing is we have the volume of the pyramid, and the big one, and they've given that as 28. And then we are also asked to get eventually EABPQ, correct? EABPQ, okay. And then we are also told a few important things, that EP over EC is 1/3, and that EQ over ED is a half. Okay, so a few steps here. The first thing is I'm going to avoid actually drawing on the diagram because it'll make it super confusing. So I'm just going to write what should be done, and you guys can draw it and sort of visualize it 3D. We'll draw a line PD, and then you'll see that you'll have A, B, C, D, P, and you'll have P, A, Q, D. And then you also can look at any pyramid and calculate its volume as follows: 1/3 times the base times the height. So the area of the base times the height. All right, so that is just very preliminary stuff there. Most of it already given to you in the question. Okay, so that we'll call that part 1. Part 1. Now part 2 is we're going to look at A, B, C, D, E. That big guy is actually A, B, C, D, P plus P, A, Q, D plus E, A, B, P, Q. And then we have a point R that is an A, B, C, D, such that symbol ER is perpendicular to A, B, C, D. And then we have another point T that we have in A, B, C, D, such that the point PT is perpendicular to A, B, C, D. And since the triangle ERC is similar to triangle PTC, PT over ER is equivalent to PC over EC. And we also know that PC is equal to EC minus EP. So therefore, EP over EC becomes 1/3. And therefore we have PT over ER, which is very important, will be PC over EC, and that is EC minus EP over EC, which is 1 minus EP over EC, which is 1 minus 1/3, which is 2/3. So let's just put that over here, 2/3. Very important. And then therefore, the volume of PABCD over the volume of EABCD is the area formula, volume formula, I should say. The same base with different heights. 1/3 base height 2. And then the bases and the 1/3 cancel, so you just get H1 over H2. And then we have the PT over ER, which is 2 over 3. And therefore, if the volume of PABCD is compared to the total, which is 28, and that, which is this guy, EABCD, right? EABCD, let's see here. Yeah, 28, I was right. And therefore, that's 2 over 3, according to what we just figured out there. Then that can easily be figured out, that PABCD is 56 over 3. And therefore, EACD is just half of that, half of EABCD. So that's 28 over 2, which is 14. All right, so moving right along, now we're into part 3, that we have EACD, which has the base ADE and the vertex C. And then we have PADQ, which has the base ADQ. And therefore, the area of triangle ADQ over the area of triangle ADE is 1/2 base times height, so it'd be DQ times H over 1/2 ED times H, and that's going to be just DQ over ED, since the other cancel out, and DQ is technically ED minus EQ, right? ED minus EQ and over ED. So that is 1 minus EQ over ED. ED, right? And then EQ over ED, we had somewhere, yeah, I think at the very beginning somewhere. Here it is. Yeah, 1/2. So that's 1 minus 1/2, and that gives me 1/2. Okay, and then finally, step number 4, this is the last step, fortunately. If we recall that EP over EC was 1/3, EP over EC was, I think, at the very beginning, yeah, right here. Then the volume of PADQ over the volume of EACD is 1/2 times 1/3, which is 1/6. And then VPADQ would therefore be 1/6 times 14, which would make it 7 over 3. And then finally, VPABCD, we had calculated that already, right? 56 over 3. Yeah, 56 over 3. And then VPADQ, we just got it was 7 over 3. So finally, therefore, the EABPQ, right? EABPQ is what we're trying to figure out. EABPQ, yeah. That would basically be the full, using which formula? I just had it somewhere here. Right here. That one. Yeah. Write that out again, actually, on the side, just to refresh your memory, that the total A, B, C, D, E was equal to A, B, C, D, P plus PAQD plus EABPQ. So we're trying to figure this out, so that's why I isolated it. And if we just use that formula, it would be 28 is equal to ABCDPQ. ABC is this guy, just the letters are a bit jumbled up. It'd be 56 over 3. And then PAQD is this guy, that'd be 7 over 3, plus our EABPQ. So if we isolate it for EABPQ, it'd be 28 minus 56 over 3 minus 7 over 3. Yeah, and then that is equal to 7.